Right, how's it going, Waals?
Good.
All right. So the way I'm planning on handling this is just kind of this is an open forum session, so I don't know if anybody else will be in or not. So just ask questions as they come to you.
Okay. So this chapter is all about hybridization, like all the sp orbitals and all of that, inner and intramolecular forces, London dispersion forces, all of that. And yeah, that's it, right?
Yes, yes. So it's basically molecules, molecule drawing, Vesper theory, theories of bonding, and then intermolecular forces,
Okay.
physical
I
properties.
I think the only thing that I really am just having trouble with is like London dispersion forces, like all the forces. I'm like, by guessing I get it correctly, but I don't really understand the differences. And I really had a lot of trouble on my like homework. That's why if you saw, like, I probably got like multiple attempts because I couldn't really tell the differences between them.
Okay, so for the different types of intermolecular forces, what you really have to go back to is the idea of polarity. So if I have polar molecules, then I'm going to have polar forces. So kind of following this through, the real question that we need to ask to do this is the molecule polar? Because if it is polar, if the answer to that question is yes, then we're dealing with dipole forces at minimum. And if it's not, then we're dealing with London forces instead.
Oh, okay. So non-polar goes with London dispersion, but polar goes with dipole.
Yes, and then we can there's further decisions we can make in this particular tree, where we can ask the question, does it contain?
And then that would be the hydrogen bonding, right?
Right. And then so, yeah.
So for the dipole, is it the one where, could you kind of explain it? Is it the one where like you have the arrows pointing to each other? Or I'm confused too.
So in dipole, yes, those are the ones where we have the arrows. And the arrows that we see have a crosshairs on them.
Mm-hmm.
This side with the arrow points to the side that is slightly negative. This side with the crosshairs on it is the slightly positive side of the molecule. And so obviously, if I have a series of dipoles from molecule to molecule to molecule, these will point themselves in such a way that we get the opposites attracting. So if I have 4 different molecules here, the positive side will orient of these molecules will orient to the negative side of this one.
And then the negative would orient to that side.
And then this side would see negatives orienting toward it. And obviously this would continue further and further and further and further.
Okay, so
um,
that's really all it was. I don't know why, but I was thinking that dipole had a more like complicated meaning because that's also how I learned polar and nonpolar using the dipoles kind of in a way.
right,
And
and so that's all it is
okay,
the the polarity in the molecule is driven by the fact that it has a dipole.
okay,
And so since it has a dipole, that positive and negative end will attract other positives and negatives accordingly. And
okay,
the total attraction of all of those molecules with each other draws the sample of substances together and makes it a lot more difficult for those substances to be broken apart. And so that's where we get the increases in attraction and therefore the increases in whatever physical properties that we're talking about.
oh, okay, okay, that makes more sense.
Now, where it gets a little bit complicated is if just because something has dipole-dipole forces or even hydrogen bonding, that doesn't mean that London forces are absent.
Mm-hmm.
London forces still exist in all molecules. It's just that compared to the magnitude of the forces that are there in polar molecules, we usually don't see them or experience them. But where they come in particular are if we are comparing two polar molecules to each other and saying which one will have the higher boiling point. Well, if they both are polar, we can't use the differences in their attractiveness to each other to compare them. We have to use their London forces. We have to use their mass. And so the heavier object is going to have greater London forces and therefore more attractiveness than the other one.
Okay, because on the quiz, I don't know why I was just mixing up when I was doing the boiling points. Because when I took my chem like intro to chem, I was also told like boiling point also depends on like the structure of your shape, and then
It can,
I was
yes.
also told it depends on your mass, and so I was confused as to like if I wanted to figure it out like without the structure, like how do I figure it out the easier way, right? So that I don't confuse myself for boiling point.
So first and foremost, look at the look at the molecular structure itself. If you're comparing two things that are polar, then yeah, it gets a little bit more complicated. Then you have to start looking at structure, shape. You have to start looking at mass. But if you're comparing things that don't have the same polarity, so a polar versus a nonpolar, well, then obviously the polar is going to have greater attraction, which is going to lower the boiling, or excuse me, lower the vapor pressure and raise the boiling point. But if they are comparing, if they are exactly the same, so I've got a polar that has no hydrogen bonding and a polar that has no hydrogen bonding, then I have to look at the molar mass. And so what I would encourage you to think about and to look at is if you haven't done your vapor pressure simulation yet, that vapor pressure simulation for lab explores some of those differences a little bit more finely.
Okay.
Because you'll get to compare polar molecules against each other, things that have hydrogen bonding against each other, and see some of the tangible differences that exist between them. You'll get to compare in the cases of nonpolar substances, how does a straight chain molecule interact with itself compared to a ring structure? And those are some of those differences that you can kind of get into. And so, like I said, that I would encourage you to, even if you don't do the entire lab, just to kind of
Mm-hmm.
look at it and kind of play with it. The simulator is really easy. It's just a drop down menu and a slider for temperature, and you can get data pretty quickly from that.
Okay.
So I would encourage you to give that a look, because that might help you with some of the visualization that you're talking about. But otherwise, it really does come down to kind of this decision tree. And the further down the decision tree you go, the more attracted to each other those molecules are going to be, and therefore the more cohesive the molecules are going to be, which is going to mean higher viscosity, lower vapor pressure, higher boiling point, um, uh, greater solubility in water.
Okay. So would you say then, like, you would say like hydrogen bonding would have like the highest boiling point?
All things considered equal, otherwise, yes.
Okay.
Because it's the strongest of the polar forces, certainly.
Right. Okay. And we won't see any van der Waals interactions or anything
Okay,
in the.
so van der Waals forces is another name for London dispersion and induced dipole.
Oh, okay.
London dispersion forces and induced dipoles are the van der Waals forces.
Oh, okay. Let's see. I think that was the main thing that I was really confused on. Just a second.
Mr. Bruck, on the review, it says like identify the binary compound that has ionic bonding. Okay, when it's talking about that, I want to say it's HCl. I mean, HCl.
Okay, let me pull that up.
Due to it having the most electrons.
Okay, that would not be the correct answer.
Okay.
Let me bring this up and share it. So if these are your options, ionic bonding, the easiest way to spot ionic bonding is for a metallic and a non-metallic component. And so to that end, lithium fluoride is going to be your correct answer, which is letter C. Hydrogen chloride does have some pretty good polarity to it, but the electronegativity difference between them is not nearly enough. I think it's somewhere in the neighborhood of 0.6 to 0.9. Chlorine's 3.0, hydrogen's 2.1 or 2.4. So if we're looking at electronegativity difference as the hallmark for determining polar versus ionic, lithium fluoride is going to have a much more larger difference in terms of its electronegativity, and that's going to give it its ionic character.
Okay.
So you said that's if you spot a metallic and what was the other one?
Metallic and non-metallic. So you're looking for a metal and a non-metal together. That's in terms of like kind of the most general and generic definition of an ionic compound. That's going to be it, because your metals tend to form positive ions. Your non-metals tend to form negative ions, and so you put the two together, and that's going to give you an ionic compound. If I have two metals together, that's not going to give me an ionic compound because one of them is going to have to be negatively charged, and metals don't do that. And if I have two non-metals together, One of them's gonna have to take on a positive charge, and nonmetals really don't do that either. It's much more likely that's going to be a covalent compound. So really the easiest way to look at it is looking for a metal and a nonmetal.
Okay. Yeah, I think that's all I had questions about.
Okay.
All right, thank you.
Oh, you're welcome. All right, Chasney, what else you got for me?
Yeah. Okay, the question. Okay, so when I see like sulfide, it's something that has to do with the ending, because I remember when I took intro to chem, it's something. If you see 8, I believe that's 4. When you see odd, I think it's like 3. Or am I not saying it right?
Okay, so it does vary a little bit from ion to ion. Generally speaking, ATE is going to have 3 oxygens. The main exemptions from that, the main examples that are different from that are sulfate and phosphate. Sulfate and phosphate are both O4, but for the rest of them, for the most part, it
8.
is ATE is 3 oxygens. So carbonate is 3 oxygens, nitrate is 3 oxygens, chlorate is 3 oxygens.
Okay, so 8 is 8. 8 is 3.
8 is generally 3. Ite is 1
No,
fewer than 8.
IDE.
IDE means no oxygen.
Okay.
IDE is that element in its natural ionic state. So chloride ion, IDE, would be Cl minus because the halogens are -1. Phosphide would be -3 because the nitrogen group is a -3 charge. Sulfide would be -2.
Okay.
So for IDE, you find that element and you pinpoint it on the periodic table, and whatever the group ion is, that's the charge it'll carry.
Thank you, because I knew it had to do with where it was positioned on the periodic table. I just didn't know how to. That's why with the last one, number 3, when you said it was LIF, I thought that you were supposed to look at the electrons, but I guess you wasn't.
Well, so the way to do it is you could do it that way. You could also look at electronegativity. And so we gave at the time there's a table out there that gives you rough guidelines for if the electronegativity difference falls between this value and this value, we consider it to be polar. If it falls between this value and this other value, we consider it to be ionic. And so you can go that way, but honestly, the easiest way to do it in these kinds of multiple choice questions is look for the metal paired with the non-metal.
Okay.
And there's usually only going to be one. And there is in this case. Lithium is a metal, fluorine is a non-metal. So put them together, that's going to be your ionic compound.
Okay. And then okay, so I'm having trouble. The former charge, when you talk about, because I've been struggling with the lab. Okay, so the formal charge, when you talk about the formal charge on a central atom, are you talking about like, because it's satisfied if it has bonds, if it's bonded to everything, so the charge would be 0. But sometimes if it's an ion like Cl minus, then the charge would be +1. I mean,
minus 1.
1. Yeah. So I mean, it'll be 0 if it's satisfied, right?
Okay, so we have to kind of dissociate ourselves from the difference between the octet rule and formal charge. So taking the example you just laid out, chloride. If I have chloride, which would have try that again.
But what if can you just do it in lines, like one straight line down, one straight line up, one like if it was a tetrahedral. If it was a tetrahedral,
Yeah.
can you do it in lines? Because that's showing that everything is satisfied. So the formal charge is 0.
Okay, so again, we need to remove, there's a difference between the octet rule and formal charge. So in our example here, chloride ion. Right now, the octet for chloride is satisfied.
Mm-hmm.
It's got 8 electrons around it. It's got a full octet. That's great. That's what needs to happen to stabilize this atom. But from a formal charge standpoint, what we're evaluating is the total charge around it. And that may not be satisfied. This may not be the best case scenario for the chlorine. It just depends. Now, again, we satisfy formal charge. Formal charge is equal to valence electrons minus dots minus bonds. So in the case of our chloride here, 7 valence electrons for chlorine minus 8 dots minus no bonds gives a formal charge of -1 on this chlorine, which is what we would have expected, by the way, because we were told this is the chloride ion, so we knew that there was going to be a charge on it. And based upon its position on the periodic table, we would have assumed it was a -1 charge.
Okay.
Now, if I look at, you said you wanted to look at like a tetrahedral. If I have chlorine bonded to a bunch of other oxygens and a chlorate ion. Let's see. Should have 7 for the chlorine, 6 for each of the oxygens, and an extra 1 for the charge. That's 26 electrons. If I take this from the straight up position of satisfying the octets for the octet rule, I end up with something like this. Right? I've got 26 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26 on the chlorine there.
Mm-hmm.
If I draw it out like this, I've satisfied the octet rule. I've done the bare minimum. But from a formal charge standpoint, this particular structure leaves a lot to be desired. Because if I evaluate the formal charge on each of the oxygens, I have 6 valence electrons minus 6 dots minus 1 bond. I've got a -1 charge on each one of these oxygens. And if I look at the formal charge on the chlorine, I have 7 valence electrons, 2 dots, and 3 bonds. I have a positive 2 charge on the chlorine in the middle. And so there's a couple of things wrong with this. First of all, it's very rare that we see any formal charge greater than 1. And second of all, every single atom in this molecule has a formal charge. Is there a way that we can negate some of that? And the answer is yes, if we break the octet rule. So if I break the octet rule, and obviously I can't break it for oxygen, but I can break it for chlorine. But if I break the octet rule and turn some of those pairs of dots into an extra bond, I can see that by doing that once, that erases this formal charge, because now the calculation here would be 6 minus 4 minus 2 for 0. And this formal charge would change as well, because now instead of 3 bonds, I have 4 bonds. And so my charge here is no longer going to be positive 2, but rather positive 1. So just this one little change helped a little bit in terms of helping with the formal charge. Now, can we do better? Certainly. We could do the same thing again on the other side. If I take out those and make it a double bond here, then I still have a -1 for this bottom oxygen, but I now have 6 minus 4 dots minus 2 bonds is 0 for that oxygen. And for the formal charge of the chlorine, 7 valence electrons minus 2 dots minus 5 bonds is 0 for its formal charge as well. The only place that I have a formal charge of -1 is on this oxygen right here. And that's fine because, again, this is the chlorate ion, ClO3 minus 1. So formal charge is different than the octet rule. The octet rule is just concerned with, do I have at least 8 electrons around each of my atoms? Because I need 8 electrons around those atoms to stabilize them, to get them to that noble gas configuration stability. Formal charge is taking a look at what does the electronic environment around that atom look like. And so sometimes it's a matter of satisfying the octet rule. Some cases we'll actually see the octet rule getting violated in order to satisfy formal charge a little bit more completely.
So of the central atom, it would be -1?
In this case, it's 0. Formal charge is valence electrons, which for chlorine would be 7, minus its dots, which in this case would be 2.
2, okay.
Minus its bonds, which in this drawing that we have, I've got a double bond here. I've got another double bond there.
So -5, yeah.
And I've got one more there. So
Okay.
7 minus 2 is 5. 5 minus 5 is 0.
Minus dots minus bonds to get the formal charge. That's what, okay. That's what I have trouble with. And then, okay, so if it was the non-bonding, It will be 1, 2, 3, 4, 5, 6, 7, 8, right? For the non-bonding.
So for non-bonding electrons here.
Yeah, so 1, yeah, but it's 8 sets. Oh, but it says out of the central, so it'd just be 1.
Yeah, so
Okay.
yeah, the central atom has 1 set of non-bonding electrons. So if I'm trying to evaluate steric number here, the steric number would be 4.
Yeah, I got, yep, yeah.
3
Yep.
bonding sets, 1 to each oxygen, and 1 non-bonding set, that lone pair. And so my shape would be, or my electron domain, my structural geometry would be tetrahedral, because I've got 4, a steric number of 4. And my molecular geometry would be trigonal pyramidal, because one of those 4 positions in the tetrahedral is a lone pair. Which I know you're looking at the Lewis Structures skill builder. I know that's not on there, but the Vesper one would be where you would address that.
Okay. So, okay. Well then, yeah, that's all. That's all I got. I'll have to look at this stuff. That's all I got though.
Okay.
For now, for this. Tomorrow, are you answering questions, or are you just doing a lecture, or there's no time for questions tomorrow?
I can give you a little bit of time either before or after, but I've got to leave here around 11:30, so
Okay.
I can't give you much.
Okay. That's fine. That's fine. That's basically what I've been having trouble with, because I keep confusing the two. But yeah, that's fine. And I got my kit. I did it yesterday.
Okay, so
I put it in order.
You put in the purchase order. Have you so do you have the voucher?
Yeah, I put the order in already.
Okay, so Carolina has it?
Yeah.
Okay, great.
Yep, I did that. It came through earlier this week. Well, day before yesterday, I think. My financial aid, so I got it in.
Okay, great.
So everything's done. So but yeah, this is the only thing, and then I'll just brush up on stuff from this the practice test. So yeah, everything's fine.
All right, good to know.
It's done. And thank you. I'll see you tomorrow.
All right, sounds good.
Okay. Bye-bye.
Bye.